on a closed curve, if you've got a conservative vector, in conservative vector fields, your network is always 0 on a closed path. Maybe. If you I mean, that's basically that theorem right there.
Something else.
All right, we're ready to move on. This is the homework. By the way, I think 2 people responded. Kieran, you did it, and who else? The assignments. I sent a Jorge, right? Jorge did it first, right? You did it first. So I sent out a discussion. I said first 3 students to list out all the homework problems that I've given out this semester get bonus points. There was 3. I deleted that one because it was a copy and paste. I could tell it was so obvious. Oh, this morning there was another one? Okay, so maybe not. All right. I could tell that the 2 of yours were different. There were little things in there, but there was a 3rd one posted last week, and it was an obvious copy and paste. So, all right. Move to the next section. We are in 13.4, Green's theorem. An entire section dedicated to one theorem. And this is a huge, fundamental result that we have here. And I think it's quite beautiful if you take a look at what it's saying. Green's theorem gives us a connection between a line integral around a simple closed curve and the double integral of the region bounded by the curve. So imagine, I'm sure I'm going to have pictures coming here soon. If I take a curve and I make it a simple closed curve, and I call that C, right? Then by default, it encloses a region, doesn't it? And that region I could call D. Green's theorem shows us that there is a connection between the line integral around this curve and the double integral of the region that it encloses. So remember, double integrals, you always had to have a region of integration. You know, we started with Cartesian, then we went to polar, right? Or we did Cartesian, then we did like type 1, type 2, then we went to polar, right? That was the double integral layout of things. Now, then we went to line integrals, and we said, oh, we're going to move along a path, and we're going to try and integrate along this path. This theorem ties the 2 together. They're actually related to each other, which is amazing. So we have to get some language down first. Positive orientation of a simple closed curve C refers to counterclockwise traversal of the curve. So if you're going to have a curve that's closed, right, then you remember the R of t draws it. Remember we came up with this, R of t was usually the vector function that would draw the curve. Then, since it's closed, it's going to go around and come back to itself. We call positive orientation when you travel along the curve counterclockwise. That's positive orientation. If you go the other direction, that would be negative orientation. All right? So like this right here. R of t equals cosine t sine t. That should look familiar to you. T is between 0 and 2 pi. That draws us unit circle, positive or negative orientation. If you start t at 0 and go to 2 pi, it's going to go and draw it this way, right? Yeah. That would be positive orientation. If you look at this right now, if you have a curve C that's oriented in the positive direction, imagine that you're on this curve, which is on a flat sheet of paper right here, and you're walking along this curve, right? I'm walking along the curve. The region D is always to my left, isn't it? As I walk around that curve, the region D is always to my left. Do y'all see that? Okay. That's another way to remember what positive orientation means. Your region on the ground that you're enclosing is always going to be to your left side. So here's Green's theorem. Let C be a positively oriented, piecewise smooth, simple curve. Okay, so positively oriented, counterclockwise. Piecewise smooth means that the curve might look like this. Okay? Maybe a bunch of line segments together, like this. Piecewise, it's smooth. So that piece, that's smooth. That piece, that's smooth. That piece, that's, you see it? So you could break up that C into a bunch of smaller, smooth segments. So as long as C is positively oriented, piecewise smooth, simple, closed, which means I can't have a hole in the middle, right? You're in the plane, which means we're two-dimensional. This, by the way, this theorem will get extended out to 3 dimensions. Green's theorem is in 2 dimensions. When we move on a little bit further, next couple of sections, we blow this out to 3 dimensions. And it's got a different name. All right? So D is the region it encloses. And if P and Q have continuous partial derivatives on an open region that contains D, then here's the relationship between the line integral and the double integral. Okay, so here's the notation we have. Remember, this was line integral? And that curve could be any curve, right? If I want to tell you that it is closed, which means it comes back to itself, initial point and end point are the same, it means a closed curve, then what I do is I draw this little circle through the integral like that, and that lets you know that that C is closed. Also, there's no way that I tell you it's positively oriented. Okay? This is assumed to be positively oriented. If I want to tell you it's negatively oriented, going the other direction, I need to do that, and we have a standard symbol for that, which is to use a little arrow on the circle that shows that you're going the opposite way, which would be clockwise. I have seen people do this before. I have seen people show the arrow showing that it is positively oriented. That's not wrong, but you don't have to have it there. But if you're negatively oriented, you have to have the arrow there to let everyone know you're going the other direction. Okay, so that's notation. And so the line integral over the closed curve C in positive orientation of P dx, so P is a scalar function with respect to x, plus Q with respect to y, another scalar function, that's equal to the double integral over the region D, which is the region it encloses, of the partial of Q with respect to x minus partial of P with respect to y. Those look familiar? Aren't those the two things that you checked when things to see if they were conservative? You would see if those were equal to each other? Yes, they were flipped, but I mean, aren't those the two partials? Okay. All right, just wanted to point that out. I think the best way to appreciate Green's theorem is to see a problem in action, okay? All right, so I have a line integral here, and I want us to compute that line integral in 2 different ways. I want us to do it using the standard way, and then the other way would be to use Green's theorem. Okay, so let's start by doing it the standard way. I have a line integral. I need to come up with the parametric representation of C. Right? So what is the parametric representation of C? It's the unit circle centered at the origin. Cosine t, sine t. T is going to vary between 0 and 2 pi, right? That's going to draw me the unit circle centered at the origin with positive orientation, right? I'd like the line integral of that. So what now? Y'all help me out. This is from 2 classes ago. Or maybe a class, no, it was 2 classes. Help me set this up. What is this going to be? You need the derivative of r? Okay, so I'm going to get the derivative of r. I'll do that here, which will be negative sine t cosine t, right? So let's do this. Instead of saying integral over c, I'm going to go integral from where to where? 0 to 2 pi. And then I need to know what y is. Well, I only have one curve here, c, right? So I need the y component of that curve, which would be sine t, times dx, which means we're only looking at the derivative of x with respect to t, which here's the x component, right? The derivative of that with respect to x, sorry, with respect to t is negative sine t. So this is negative sine t dt. You with me? Minus, so I can do two separate integrals right here if I want. But I'm going to do it all in one integral because they all have t, and they're all going from 0 to 2 pi. So I'm going to go minus, what's x? Cosine t. And what's dy? Cosine t. Now, since I decided to do one big integral, this dt right here, I'm going to move it to the back. Is that all right with you? Oh, wow. OK, that's not so bad. I can factor out a negative 1. And if I factor out negative 1, I'm going to have sine squared t plus cosine squared t, which is 1. So this is just 1 dt, which is negative t evaluated 0 to 2 pi. So your answer is negative 2 pi. All right, that wasn't so bad, right? Questions? I wonder how long that took. You ready for the second way?
Yes.
All right, here we go. So the second way is to use Green's theorem. Green's theorem says that the line integral over positively oriented curve C of p dx plus q dy is equal to, so I'm going off the previous note, just so you all know when I refer back to it, I'm looking at this right here, right? This right here. This is equal to this double integral. Which should be the double integral over d of partial q with respect to x minus partial p with respect to y dA. We're integrating with respect to area because it's a double integral over a region, right? So the big difference here is that instead of trying to look at the curve going around the region, we're going to actually look at the region itself. So do we know anything about this region? Well, I do, right? I do have some idea of what that region looks like. But let's just look at this partial real quick. What is P for us? I guess I want to write it up. Isn't this P and this is Q? Do you all understand? So P is X, isn't it? And Q is what? I'm sorry, why did I do that? P is Y. And Q is what? Negative X. Be careful, because in the formula, it's plus Q. So you'd have to change that to plus minus X. OK, what is the partial of Q with respect to X? What's the derivative of this with respect to X? Negative 1. So check it out. D, right? This is negative 1. And then minus the partial of P with respect to Y. 1. So minus 1. dA. You all good? Which is negative 2 double integral over d of 1 dA, right? You okay with this? Anybody know what that is? That's the area, right? Remember, there's a very special property. The double integral of 1, right? This is the area of what? Area of D. What was D? The unit circle. What's the area of the unit circle? Pi r squared? What's the radius of the unit circle? What's the area of this? What is this then? Pi. The answer is negative 2 pi. Do you see how easy that was? We didn't even have to do this integral because we know it represents the area of D, and if D is the unit circle, we're done. Isn't that awesome? No? Am I the only one who thinks that's awesome? Now look, if you didn't recognize that as the area of D, then what you would have to do now is actually come up with how you're going to define this region D. And I think most of us would say, oh, that's polar, right? You say, okay, for polar, my theta is going to be between 0 and 2 pi. And then my radius is going to be between, what, unit circle, 0 and 1. And then this double integral down here becomes negative 2, integral from 0 to 2 pi, integral from 0 to 1. And what are you integrating? 1, but you went to polar. R d theta. You remember, you always have to remember to pop the r in there. And then if you go through this, all of this right here, and you do that, you're going to get pi at the end of it all. And then you'll get negative 2 pi. But that's much cleaner if you can see that, right? Okay. Awesome. I should just let you all know, I'm going to be pretty busy the next week or two. I'm on a hiring committee, so we've got all these hiring meetings. And then I have to do these faculty evaluation things, and I'm just going to be really busy the next couple of weeks. And I'm good. My plan is to continue to hold office hours as normal. Okay, so nothing should change in terms of office hours. It's mostly what's happening after I get out of class. So like after this class, I have a 3 o'clock meeting. I'll be in until 5. So just FYI. All right. Here's another one. All right, so here we go. We've got evaluate this line integral, positively oriented curve C. Here it is. Oh my goodness. That just looks nasty, doesn't it? Doesn't that look bad? C is going to be a circle with radius 3, right? So let me draw C real quick. It's closed, right? It's positively oriented. Well, I can draw it positively oriented. To do that, I need to come up with my vector curve, which would be almost the same as what we just had, but 3 cosine t, 3 sine t. And t is going to vary between 0 and 2 pi again. That all okay? And we're going to need the derivative in there, aren't we? Because we got to put in like dx and dy, so we've got to have derivatives. That's okay. I'm not intimidated by this yet. Negative 3 sine t, 3 cosine t. But then I have to rewrite that whole thing now, right? Okay, so let's write it. This will become integral from 0 to 2 pi. All right. 3y, which for me would be, what's wrong?
Oh, no, I was just wondering, is that, are we still doing Green's?
Oh, I'm sorry. We're doing them both ways.
Oh.
We're going to do it both ways. So you can see why Green's theorem is worth having. Okay, so look at this. What would 3y be? 3 times, what's y? Sine t, so 3 sine t again, like that. That's 3y minus e to the sine of x, but what's x? 3 cosine t. All this times dx, which is